Hello and welcome. We have a problem here where we have a 1500 gallon rigid tank, and in this tank is filled with H2O, a liquid vapor mixture, and the initial temperature is given to us. The mass and volume are known, and then the tank is heated to a final temperature of 200 degrees Celsius. We have to find the mass of the liquid in the tank initially, the change in pressure, of course the pressure will increase as you can imagine, and the amount of heat transfer. Okay, so how do you go about it? You know that to find the pressure, which is a property of the fluid, we need to find the state of, so state 1, we already know the volume and mass, so we know one property will be specific volume by mass, but we need two thermodynamic properties. What is the second property? The temperature. So therefore, from these two, we can find out everything about state 1. For state 2, we know that, so these are our state 1 conditions. State 2, we know that temperature is given to us, 200 degrees Celsius. We need something else. If you read the problem again, you realize what else we know about state 2. The tank is rigid, so you can see that the volume 2 must be equal to volume 1. The volume cannot change. Also, the mass, M2 must be equal to M1, right? There can be some liquid converting into vapor because we are heating it, but the total mass cannot change. Even if there is a chemical reaction, mass cannot change, right? This is conservation of mass. So this is the fundamentals that once you know, so therefore these two will give us specific volume. So we know two thermodynamic property of the final state. Therefore, we can calculate the state. Now let's go launch an app with which you can solve this problem. I have already logged in as a student, test apps, and we'll go, we are going to find properties of states, and of course this is a system state because we are trying to find properties of H2O in a rigid tank. Okay, so to launch it, we click system states, and of course the phase change is a possibility. Being a possibility, we launch the PC model. To launch the app, you go to the leftmost tab, and there we go. So the first thing first, we could be tempted to just try entering mass here, like mass is 10 kg, and go on like that. A better way to do this is to go to the I/O panel and list all the variables. That way, we will have control over every variable on the problem. So we'll say mass in kg equals 10. Again, m is a standard symbol, so variable begins with m. We better write a comment that given variables, this is a comment line. And the first is mass kg equals 10. Notice that when you click the calculate button, it will format it nicely. And also it is registering what mass is. So if you go to the output panel, you can see mass has been registered as 10 kg. If you want, you can come back here and write down equals m kg. So now the variable has been picked up. If you put the pointer over M1, you can see the mass will show up in this help panel. So to reduce the time, what I have done, I have already entered all the variables that is given in the problem. These are the 4 variables given in the problem. I have also taken the time to write some comments, different blocks of the code. Mass of the liquid you have to find. Part B is calculate the change in pressure. And part C is how to find the heat transfer in this problem. We'll discuss each of them as we proceed with the problem. So let's go enter all of this in the state panel. For state 1, what we know is the mass in kg, volume in gallon. I think I defined the variable as gallon. But notice we have to pick the correct unit here. If gallon is not present, we have to convert it to something that is heat present, so we just gallon. So in other words, that if we don't pick gallon, then this number will not reflect so many gallons. It will be something else. So if you calculate, just to check, oh, so you see the white background means it cannot understand this variable. The reason is that I declared these variables here, but I didn't calculate, so they don't appear on the output panel. If I click the calculate, now the variables are known to all the panels. Now I can go back there, and if I do a calculate, they are now understood. So if you put the volume pointer over volume, you can see it's picked up as 1500 gallon, which is the correct amount. Finally, what we know is the temperature, I believe. Yes, T initial. So we enter that, and that will complete our state 1, T initial degree C. The unit here is already degree C, so we don't have to worry about that. Calculate, and therefore you can see pressure at state 1 has been found, and you can see that there's equality. That means it's a two-phase mixture. Okay, going to state 2, water given. We know that mass will not change in this problem, and volume will not change in this problem. As you can understand, these two together will produce one thermodynamic property specific volume. Well, density also, but they're inverse of each other, so this is not really two independent properties. The second independent thermodynamic property, the blue property, all thermodynamic properties are labeled with blue colors, is known, which is T final degree Celsius. That's the variable name, and so now state 2 is known. Okay, for the rest of the work, we go to the I/O panel and see how do we find the mass of the liquid. So first, let's remember what quality is. Quality is mass of vapor in kg. We can find out will be what? In the initial state, mass of vapor, I can write if you want state 1 or just kg equals total mass times the quality, and that will be the vapor mass. If I do a calculate, the vapor is about 6.36 kg. So how much liquid there? M liquid kg equals M1 minus M vapor kg. As you can understand, the vapor and liquid, which are in coexistence in equilibrium together at state 1, are saturated. So a better name for the variable could be M set vapor, set liquid, SAT for saturated. But anyway, this kind of is more readable. Now calculate the change in pressure. We know delta, capital delta, is our engineering symbol for change. So I'll call it delta pressure in kPa equals P2 minus P1. If I calculate, so I found part A answers. Part B, what we have? Oh, sorry, that was the part B. First part was finding the liquid mass. And part C is a little bit difficult because it involves energy analysis. How much heat has been transferred? So if you go back to the problem and think about it, heat is the only way energy is being transferred in this problem, right? There is no work. Of course, there is no electricity crossing the boundary. There is no shaft crossing the boundary. And the boundary is rigid, so there is no boundary work either. So therefore, heat is the only way energy is entering the system. Well, we don't know how to calculate heat transfer. That is covered in a different class. But we do know, if we can somehow know how much energy in the tank, how much the energy increased, that must be because of heat. So suppose there was 100 amount of energy in the tank, and I put in 20 amount of heat. Then the final energy will be 120. Put another way, if I know the final stored energy and initial stored energy, the difference must be the heat supplied, must be the energy supplied. And heat being the only way energy is being transferred, we are ready to do an energy analysis. So what we do here, we'll first write down E initial kilojoule would be what? M1 times E1 small e1. Remember, small e is the symbol for specific stored energy. So we multiply we multiply that by mass, so therefore we get the total initial stored energy. What is the final stored energy? We're almost done in a couple of seconds here. E2, right? Of course, M1 and M2 are equal. By the way, you can click this, then enter will work as calculate. So therefore, we understand that the change in delta E kilojoule is what? Is final stored energy minus initial stored energy. And we have found the increase in stored energy, and therefore Q in kilojoule would be equals same as this. And I think the problem said find it in million joules, so we can write Q in million joules must be equal kilojoule control V divided by 1000. And you can see that the answer has been obtained, 8.55 million joules. So we found the answers of each part of this question. Sometimes it's a nice idea to just write a comment at the end of the line. Suppose you want to say how you came to this. You know, we know we did an energy analysis, but you can also mention that the cause. You can just have a little explanation here. Heat is the only way energy can increase. So now anybody reading this code can easily understand what is going on. And just to mention, suppose let's remember this answer, 8.55 million joules. Suppose the question was the final temperature was not 200 degrees Celsius. Suppose I heated it to 300 degrees Celsius. What will happen? You change it to 300, click a calculate button, that updates, that means your new value is registered now, and all you have to do is to click on the super calculate button, and all the results are updated, and you can go to the IO panel here, right here, and you can see the new answers. The heat input is now 10 million joules. So this is the beauty of writing a code, that the concept is now in a few lines of code that you have total control over, and you can change a known variable as a parameter and kind of parameterize the problem. Imagine the possibility that as a real life engineer, you probably will care more about what will happen if the temperature keeps increasing. Will the tank explode? So you can draw a plot of how the temperature rise will cause pressure rise and many other things. So this simple problem can be converted into a big practical project. Okay, I'll stop here.